Welcome to another video on the 2022 NECO Physics Practical. In this video, our focus will be on the mechanics section of the practical. Let's take a look at the apparatus that will be given to you. You'll be given a G-clamp, 2 meter rules, an optical pin, a mass hanger of 50 gram, 4 masses of 50 gram each, a beaker, water, plasticine, and retort stand. The goal of this experiment or the objective based on this apparatus is to determine the Young's modulus of a meter rule. Although this experiment I'm going to explain will not make use of the following. We're not going to make use of the following apparatus, that's beaker, water, and plasticine. And the reason why we are not going to make use of them is because of the following reason. Number one is this apparatus might not be relevant. It may just be a kind of distraction, right? It may not necessarily be used in the actual experiment. Then the other possibility is that it might be used, but it might just be used to reduce the weight of the masses. In other words, it's possible that the mass will be immersed in a beaker filled with water, right? Then the plasticine is just a clay-like material that is typically used as a base for beaker. So that's what the plasticine is. That's what the plasticine is generally used for. It's a synthetic clay that you can use to mold any shape. Then in the case of physics lab, they typically use it as a base for breakable wares like a beaker, for instance. So what I'm saying is this: if these three apparatus will be used, it will have a minimal effect on our overall results. It will just serve as a means to reduce the weight by by the effect of upthrust, right? But there are two possibilities. Either these three apparatus will absolutely not be used during the actual experiment. They're just redundant or a sort of distraction, or it might be used, but this time around to just serve as a means to minimize or reduce the weight, right? So whatever the case may be, it's not going to affect the core theory behind what I'm going to explain. So throughout my explanation, I'm not going to use beaker, water, and plasticine for the reasons that I've stated. So from what I can deduce from this apparatus, the goal is to determine the Young's modulus of one of the meter rules. I will explain in detail why that's the case, and we're going to check the diagram behind this experiment, and we're going to also look at the theory behind it. So let's start off with the diagram, the experimental diagram. This is the experimental diagram of this mechanics experiment. Here you have your G clamp here. You have the G clamp here. And the G clamp is meant to clamp one of the meter rules to a bench, a bench in the lab, right? Then you have a retort stand suspending another meter rule. Then you have a pin connected to the end or tied to the end of the first meter rule here. The goal of this pin is to indicate the depression after applying this mass. So that's the goal of this pointer. Is a pin just to tell you where the current mark is. Then you have your weight hanger together with the mass, right? Then you have your retort stand, and that's it. That's basically this is just the experimental diagram. So let's analyze what's going on here. So here is how the experiment goes. This is the meter rule, the first meter rule, right? This is the first meter rule. Then let's assume the clamping happens here, right? The clamping happens here. So here is the length that we are dealing with here, the length of the meter rule. Then the assumption here is that the weight is hanging from one of the ends, this edge, right? That's where the weight is hanging from. Then the pointer is just to tell us where the value is along this meter rule. So let's say the current reading when there is no weight is, let's say when there is no weight, right? When there is no weight here, let's say the initial reading is at 20 centimeters, right? Let's say it moves from 0 here to 100 centimeters. So let's say it's at 20 centimeters. By the time you apply some, by the time you add some weight to this weight hanger, by the time you hang the weight hanger and you add some weight, this is what you should expect to see. You should expect to see a kind of scenario like this, where instead of you having a straight meter rule, it bends. So if this is the original meter rule, right, the new meter rule will be something like this. So you have a kind of bent meter rule. Bent meter rule, where the origin, this is the bent meter rule, right? So let's say the original meter rule is this. The bent meter rule will be somewhere here. So now what's going on here is the pin might now point towards this point. So let's say originally this is 20 centimeters. This might be somewhere like maybe 20, let's say 4 centimeters, for instance. So it means you now have a kind of depression. So this is called a depression D. We're going to denote the depression as D. So originally we have 20 centimeters, but now with a weight hanging at the end, the new the new the pin will start pointing somewhere here. Probably let's assume 24 centimeters, for instance. So now you are going to measure this depth D, this depression D, right? And you're also going to measure the total mass, right? This is the mass here. So the way the experiment goes as follows. You take note of the initial location of this pointer before adding any weight or any hanger. Then once you add the hanger, the meter will depress. In other words, we bend downward, going down a little bit, and the pin will start pointing a little bit downward. And here you're going to have a new location for your pointer, let's say 24 centimeters. So the difference is now the D. So this is how the experiment goes. So let's take a look at how the table of reading is going to look like. So here is how the table of reading is going to look like. So here's the table of reading. This is how it's going to look like. So the first thing you'll be told is to note the initial location of the pointer. Let's call it D naught. So D naught here could be something like 20 centimeters, 20 centimeters, maybe 20 centimeters all through, right? Then the next thing you'll be told is to note the weight of the hanger. So the weight of the hanger is going to be something like, in from the apparatus we are told that is 50 gram. So the weight of the hanger, let's call it M naught, is 50, 50, 50, 50, right? Then the next thing is to add a given mass. So let's say you have a mass, let's call this mass M1. So let's say we add a mass of 50. By the time you have 50, what is the new location of the pointer? So we call that D. You can call that D or you can call that D1, right? So let's call it D. So in this case, we are going to have, let's call it D1, right? So D1 will be reading 24. Then you'll be told to look for the total mass, the total mass. So in this case, total mass is something like the M1 plus M naught. So M will be 100. Then you'll be asked to calculate the difference. So D is something like D1 minus D naught, right? So that will give you 24 minus 20, and that will give you 4. So now this is just for the first reading. So for the second reading, you increase the mass. So instead of 50, you're going to have 100. Then the total mass will be 150. then you calculate the D1 and the D. Then here I'm going to add another 50 because you have 4 masses, right? So here will be 150, and here will be 200. So this is how the experimental setup is going to look like. You may also have a case where the mass is 0, the M1 is 0, you just have the weight hanger and all of that, but this is what you should expect to see. Then after doing all of this, you will be told to plot something like this. You may be told to plot M on the y-axis and D on the x-axis. Then your graph should be something like this. Your graph should be something like this, and you'll be told to determine the slope, and that's it. So this is what I strongly believe would be the nature of the experiment. You may also be told to have the D on the y-axis and the M on the x-axis, so but it doesn't really matter. But this is how you should expect the experiment to go. So the question that may be on your mind is, what is theory behind this experiment, and why do we have this kind of setup, and what does it relate to basically? That's what I'm going to explain in the next slide. In order to understand the theory behind this experiment, it's important I explain some concepts around Hooke's law. Now, what's Hooke's law? According to Hooke's law, if you have a particular spring, let me use a spring or a material. Let's just say an elastic material. It could be a rubber, for instance. So let's say you have a material whose length is L, right? And let's say that material has the following property. Let's say this cross-sectional area. So let me draw the material this way so that it will be much clearer. So let's say I have a material of this kind. Let's say the material is of this shape. The original length is L, right? And let's say we decide to apply force. And let's say the cross-sectional area is A, the area of this cross-section. Then let's apply a force F. If you apply force F, you are going to elongate this material. So let's say we have a force acting along this direction. And now let's call it L2. This is L1 and this is L2, right? According to Hooke's law, if we calculate the extension is simply the final length minus the initial length. According to Hooke's law, the force you apply is proportional to the extension. In other words, the higher the force, the higher the extension. That is basically what Hooke's law says. There's a direct relationship between the force and the extension that will be experienced by the material. Then if you want to get the exact equation, you say F equals to Ke, where K is known as the stiffness, the stiffness or the force constant, Okay, so it means the stiffness, which is K, is equal to F over E. So we're going to talk about stiffness in detail later, but now one thing you understand about stiffness is a property of not just the material but the structure. So what that means is, for a given material of a given shape, the stiffness is constant, is fixed. So what that means is, if I have a particular material that I know the length, I know the area, then the stiffness will be the same. But if I change the area or I change the length, the original length, then the stiffness may not be the same. But we'll talk about that when we want to differentiate it from Young's modulus. Now, what about stress? The stress on this material is equal to the force you apply divided by the cross-sectional area. What about the strain? The strain on this material is the extension divided by the original length. Then What about Young's modulus? Let's call this Young's modulus Y. Young's modulus is equal to the stress divided by the strain. So what this means is you can relate the force, the cross-sectional area, the extension, and L1 as follows. It means Y is equal to F over A divided by E over L1. So if you try to rearrange this whole thing, you're going to get something like this. It means F over A is equal to Young's modulus times E over L1. So one question that may come to your mind is, note that Young's modulus is a constant for a given material. So one question that may come to your mind is Young's modulus the same thing as force constant? Or how is Young's modulus related to force constant? So let me talk about that in the next slide. We derived the following equation. We know that the force applied to a given material is equal to the force constant times the extension. We also know that the force divided by area is equal to Young's modulus times the extension over original length. So we want to answer the question of, is Young's modulus the same thing as stiffness? So this is how you should think about it. The stiffness is the resistance that a material uh, produces when a force is applied to it. It's more or less like the resistance to deformation. So if the force constant is high, it means that material has a very high resistance to deformation. It doesn't easily deform. If you try to stretch it, it hardly stretches. If you have a very low force constant, it means you can easily stretch a spring, for instance. They have a very low force constant compared to metals, like very, very hard metals. So now the question is, how does that relate to Young modulus? Because Young modulus is also some form of resistance to deformation. So why are they sounding the same, but they are different? Because if you try to look at this formula, Young's modulus is not exactly the same as K. So the question now is, how are they related? So let's derive the relationship between them. If you make K the subject, you're going to get something like F over E. Here, try to derive F over E. If you derive F over E, you're going to get something like, make F the subject first. You're going to get something like this. Then try to take E to this side. You're going to have F over E equals Young's modulus times A divided by L1. You can see that we can replace K here. K is now equal to Young's modulus times cross-sectional area divided by original length. So what this means is K is actually a function of Young's modulus. It means K increases with increase in cross-sectional area and K decreases with a decrease in the length. So what this means is the Young's modulus is a constant of a material irrespective of the dimension. That is, dimension does not affect Young's modulus. So this is what it means. If I have a wooden plank whose length is, let's say, 10 centimeters, and I have another wooden plank, the same material, whose length, let's say, is 100 centimeters, the Young modulus here is the same thing as the Young modulus here. But what about the stiffness? The force constant here is not the same as the force constant here. Not the same, because the length of the material is different. But if I have the same length, then the force constant will be the same. So it means the geometry of a material that plays a role in determining the force constant. The geometry does not play a role in determining it. It is the nature of the material that determines Young's modulus. So that's why Young's modulus is much more important to builders and engineers than force constant. Force constant is a function of the geometry of the material. And if this cross-sectional area is also different, so if I have a material of this kind, let's say the cross-sectional area is this, and I have another one whose cross-sectional area is very large. What this means here is, since the force constant is directly proportional to cross-sectional area, it means this we have a much higher force constant than this. If they have the same length, for instance, this will have a much higher force constant than this one. And this is how you should think about it. If I give you a particular rubber, for instance, and the rubber happens to be very wide in cross-section area, if you try to pull that rubber, you exert a lot of force to stretch it just by a tiny amount compared to when the rubber is very thin. If the rubber is very thin, you can easily stretch it. And anything you can easily stretch indicates that the force constant is very small. The same thing goes to length. If I have a very long plank, have you noticed that if you sit on a very long plank, it tends to bend easily? Or if you try to stretch something that is very, very long, you notice that they tend to stretch easily. If you check a building, where the build construction site, you'll see the iron rod they typically use, very thin and long iron rod. You see that those iron rod, they easily dangle, and they dangle easily because the force constant is low. Because when you increase the length, you decrease the force constant, right? They are inversely proportional. And that's the reason why iron rods you see in construction that they dangle easily compared to a very small piece of iron, which will not dangle easily. So, in summary, both force constant and modulus, they are they are some sort of constant that determines how much resistance to deformation a material will pose to an applied force, an external force. But the difference is modulus is not affected by the geometry of the material, whereas stiffness is the value of the stiffness is also a function of the type of material and the cross-sectional area and the length of the material. So now we've talked about all these terms that you come that you are meant to come that you come across in this experiment and also in other aspects of physics. Now let's talk about the experimental equation. What was the equation governing this experiment? Now that you understand the theory behind it, let's take a look at the equation behind this experiment. As we discussed earlier, this is the first meter rule, which is hanging on a G clamp, and you have a weight hanging at one end. And here you have a meter rule that tells you where the pointer is. Then the distance between the original state of the meter rule and the new pointer is D, which is known as the depression. Now let's analyze this meter rule. This meter rule has the following information. We know the length. So let's say this is the length, right? The length is the distance between this point and the original point where it is. Just the length of this meter rule, basically, the original length from the G clamp to the tip. Then we have the breadth. So let's say this B represents the breadth of this meter rule. That's this distance. Then here is the thickness. Let's call this thickness T, right? This thickness T. What equation connects all of this? And let's say this is F. This is the force acting on the weight hanger. So what's the equation that connects all of this? The equation result is from a theory known as bending theory. So it's a theory that analyzes objects that bends under this kind of force, right? The equation governing all these parameters is given as D equal to 4 times F times L raised to the power of 3 divided by the Young's modulus times the breadth times the thickness raised to the power of 3. So that's the equation governing this experiment. Now think about it this way. It means the depression is equal to 4 times the force times the length raised to the power of 3 divided by the Young's modulus times the breadth times the thickness raised to the power of 3. Now, how can we connect this to the mass and all of that? We know that force is equal to mass times the acceleration due to gravity. So we can say this is equal to 4 times mg and L raised to the power of 3 divided by Young's modulus times the breadth times the thickness raised to the power of 3. So what this means is if we make m the subject, it means m is equal to Young modulus times b times t raised to the power of 3 divided by 4 times g times L raised to the power of 3 then times d. So from this equation, we can say that the slope is equal to the whole of this. So the slope therefore is y times bt raised to the power of 3 for gl raised to the power of 3. So this is the equation governing equation. M is directly proportional to d. There's no, you don't expect to have any y-intercept. The y-intercept is 0, right? So that's why your graph is going to start from 0, basically. Okay, then the other thing you need to note is in case you were told to measure the value of the breadth, you may be asked to determine the value of b and also the value of phi, which is the thickness. If you happen to know that value, you can determine the Young modulus as follows: as the slope times 4gl raised to the power of 3 divided by bt raised to the power of 3. So this is the Young modulus of the meter rule, given that you know the slope, where s is equal to the slope of from your graph. Although to get the exact result, in other words, to get the exact Young's modulus, you might want to, you may be asked to multiply some factor that will make the equation have the same unit. But this is generally what you should expect to come across in your experiment. So before I end this video, I would like to talk about some of the precautions you should put into consideration. One of them is ensure that you avoid error due to parallax when reading from the second meter rule, because you are going to take note of where the pointer is indicating where the pointer is. So make sure you avoid error due to parallax when taking reading from that. Then another thing you want to do is ensure that the meter rule is not oscillating. That is, this first meter rule is not oscillating. If it's oscillating, this pointer will not be stable. So ensure that it is static before taking reading. Then another precaution you should take note of is avoid droughts. Ensure there's no fast moving air when performing the experiment so that the effect of the moving air will not contribute to the reading. So these are some of the errors you should take note of during this experiment.